Okay, I can start, yeah? Do you hear me? One, two, one. Just up your hand.
Yes.
Thank you, thank you. Okay, my topic is related to the quantum physics and a little bit with Zarina's topic. It's the from the journal Progress in Quantum Electronics, and today we will see like the new technologies that approach in the quantum physics and in our world. Okay, the topic name is uh, hybrid classical quantum communication network, and just an overview to this. Okay, in these papers, we review the integration of communication protocols into existing fiber optic networks, exploring how classical and quantum systems can coexist and benefit from each other. And the main goal of this topic is to leverage the widespread classical infrastructure for emerging quantum technologies, reducing implementation costs and paving the way for a heterogeneous communication network that seamlessly support both classical and quantum communications. In the simple words, just imagine the today's communications like the internet, the mobile networks, the Wi-Fi, and these all communications that I said before, so like tools, create the classical networks that we use today, right now, for example. And they send information to us by using the electric signals, radio waves, fiber optics, and etc. And next one, you need to imagine the quantum networks. Yeah, quantum networks is networks which transmit information using photons in quantum states, which we can also describe like qubits. What is the qubits? For example, we have just a simple bit. Uh, as you know, in the uh, computer's language, yeah, like program language, we have the like informations like kilobyte, megabyte, and the byte also divided to the bit, and the bit is just the like random number of the one of the or zero. And what is the difference with the qubit and the just a bit? The qubit is work by the superposition principle. Superposition principle, as you know, it's like plus and minus both of the one in the time. And here we just have one and zero in the one time. So it's like used qubit. And back to those words that I said before, the quantum networks is a networks which transmit information using photons in quantum states like qubits. Okay, and why the topic is called hybrid classical quantum communication networks? Because uh, we in this state like use both of them to coexist. Yeah, and take the benefit from the each other. Like it's more simply to build another building from the old fundament to just create new fundament. I hope you understand. Okay, let's move on. In this graph, uh, I hope you see. Yeah, here you can see the like BL. to the ear, and the many like communication tools. The first one, as you know, is the uh, telegraph. And what is the BL? It's bits divided by S to the kilometers. What is mean? It's like the information that we can share it to the some distance. And as you see in the graph, this number is like increase during the years by using uh, many other tools. Так, okay, like telegraph in the 1550, yeah, 1850, sorry. Telephone in the 1900, like coaxial cables, also the microwaves, yeah. And the next one is the optical fibers, like that used to wide to the communications like networks that we have today with DM and the CDM right now. Okay, let's move on. Okay, the vision of the heterogeneous communication network. So that's it. For that, we need to like use the benefit from the both of the communications. For decades, global classical communications network have transformed society. Concurrently, quantum networking has emerged with potential applications in distributed quantum computing, quantum sensor networks, and the secure communications. Yeah. Instead of building quantum networks from scratch, a pragmatic approach is to integrate quantum communication protocols such as quantum key distribution into existing fiber optic infrastructure. Okay, as I said before, it's more easily to build in the fundament that we have right now. uh, this part of the text is about them. Yeah, and what is the QKD, like the quantum key distribution, and what is the goal of this term? Okay, let me just read the first one. The reduced cost, sharing optical fibers, hardware, and network controls resources significantly lowers explanation expenses. Next one is mutual benefits. Classical communication will eventually benefit from quantum innovations like quantum memories and the repeaters, and the future internet. A seamless integration of classical and quantum communication is envisioned for the future internet. Uh, like how works this the heterogeneous communication network systems? We have here like two parts. Is the classical parts that we have right now. It's a routing, user identification, for example, message delivery, and regular data transmission. And the second part will be the quantum part. And here, what is the quantum key distribution? I said before is like some passwords, yeah, passwords and secretly like secret information that will get some person. And the main advantage uh, of this quantum key distribution it's that for example some hackers, yeah, never will get your information because as I said before, this quantum key distribution is working in the qubits, and the qubits it's on the superposition, like we don't know here one or zero. Yeah, they're both of them. So this helps us to like save some passwords from the uh, others' hands. Yeah, and the next one is the teleportation of quantum states. Yeah, that's all for the QKD. Okay, next one is the evolution of communication networks. The history of optical communications dates back to ancient civilization using smoke signals and beacon fires. However, widespread long distance optical communication only became feasible after the development of ultra low loss silica fiber in 1970. Since then, the information capacity of fiber networks has grown um, exponentially. Yeah. The first one is uh, regenerated direct detection era is extended communication distance using classical regenerators, primarily limited by transceiver bandwidth. Next one is amplified dispersion managed era. It's widespread uh, adaptation of VDM and optical amplifiers for cost-effective and scalable solution. Um, Third one is amplifying coherent communication era, introduction of coherent optical receivers, enabling longer generator spacing and improving electrical efficiency. Like looking ahead, parallel spatial pass through space, division multiplexing present a promising solution to meet the exponential demand for data transmission. Okay, let's just move on. I have no comments for these slides. I guess it's understandable. Yeah, yeah. Okay, next one is fundamentals of optical communication systems. Like here is a figure how it works. Atypical communication systems consist of transmitter, receiver, and communication channel, as we know from the lessons of like microelectronics or the others. Information is encoded, transmitted, and then decoded with the various techniques employed to ensure efficiency and the reliability over long distance. Okay, here as you see we have both sides. Like the first one is transmitter side, and the second one is a receiver side. Okay, the transmitter side source encoder compressing path messages to enhance communication efficiency, reading data with minimal information loss. The channel encoder introduces redundancy for error correction, crucial for reliable data recovery in lossy and noisy channels. Uh, Modulation is the data is transferred from electrical to optical domain by modulating light source properties. And the light source early systems used LEDs, yeah, like the fire, yeah. Modern coherent VDM systems employs narrowband source for higher data capacity. And for the receiver side, it's a optical detector converts received optical signals back to into electrical form. Uh, Next one is direct uh, detection. Yeah, photo detector measures intensity losing phase information simpler to implement. And the coherent detection received optical signals based with the local oscillator to recover both intensity and the phase information. I mean, and for long distance communication due to in the headset spectral efficiency and the in-string filtering. Okay, is the evolution from broadband source to narrowband and from direct to coherent detection, and highlights the continuous effort to maximize data carrying capacity and improve system performance. This all needs to create like the future internet in the simple word. Okay, next one is fiber loss management. Yeah, fiber loss and chromatic dispersion are two critical factors limiting the range and the speed of fiber optic communication that we have now, and overcoming these challenges has been central to the exponential growth of network capacity. Okay, uh, in the left side we have the fiber loss management, and in the right side is the fiber dispersion management. In the left side is the impact of them. Well, let's start. Optical signal power decreases exponentially with fiber length, restricting communication distance. And the low loss fibers is the commercial silica fibers achieve attention below of the 0.160 decibel per kilometer with ongoing research into hollow core fibers for further reduction. And the regenerators is restore degraded signals by re-amplification, reshaping, and reteaming. And regenerations were initially used by post challenges in modern VDM networks. Next one is optical amplifiers. It's used to amplify the entire VDM band optically, making the like channel transparent. Yeah. In beam doped fiber amplifiers, it's widely developed, deployed overing the 20 to 30 range decibel gains and extending transmission distance up to 100 kilometers. And there's a noise like shum, yeah. Optical amplifiers introduces amplified spontaneous emissions, degrading the signal to noise ratio. The theoretical minimum noise figure for GDFAS, yeah, it's erbium doped fiber amplifiers, is this real yeah, decibel. And fiber dispersion management. The impact of them is chromatic dispersion because differences frequency components of light pulse to travel at different speeds, leading to pulse broadening, broadening and intersimple interferences. Dispersion shifted fiber or DSF introduced to achieve near zero chromatic dispersions at 1550 nanometers. But problematic is that in the VDM networks, due to non-linear interactions like four-wave mixing, yeah, this term is it's like little complex, but if we like research it in the just overview, it's more simple than their name. Yeah, non-zero dispersion fibers or NSDF is a modern system since use NSDFs with carefully managed dispersions. Uh, Characteristic is cascading fibers will with opposite dispersion signals to balance overall dispersion while suppressing non-linear effects. And as a high-speed challenge, as transmission rates increases, pulse duration shortens, and spectral width uh, broadness. Uh, okay, let's move to the next slide. Here we have like information about the multi user light wave networks, and the multiplexing strategies, and the shortly information of about the VDM, SDM, TDM. Okay, optical fibers supports multiply degrees of freedom for low loss transmission. Yeah, low loss transmission is means that we don't lose any information during the transmission. Some information in the for example, quantum networks. We also will have this like the problems. I guess I will yeah answer to it in the next slides. Yeah, enabling various multiplexing techniques to accommodate multiply users over shared cables. These strategies are crucial for optimized networks resource allocation. Okay, let's move to the for example for VDM, which means like wavelength division multiplexing. The leading method for supporting multiply users dividing into co- cores, yeah, CVDM with 20 nanometer channels and the dense to with tighter channels spacings. Elastic or flex grid TVDMs allows variable channel width for precious bandwidth allocation. Okay, what is the next one? Is SDM. It's a space division multiplexing. It's assigns users distinct transfer spatial model modes in multimode or multi-core fibers. Offers potential orders of magnitude increases in transmission capacity for space constrained high bandwidth links. And the third one is the TDM or time division multiplexing. It assigns user slots in the time domain, typically interleaved. It can be electrical or optical. Optical TDM enables higher total line rates but faces technological challenges. Yeah, the main problems of the all networks that we have is like technological challenges and I guess for example this hybrid connection like with classical and classical networks and quantum networks hybrids it will be in the long time future because of the technological challenges. I guess the main challenge will be like we don't have enough money to make that. Okay, this multiplexing approach aligns with all optical signals processing techniques aim to leverage the ultra high bandwidth or optical signals and reduce reliance on optical electrical conservation. Through practical implementation faces significant hurdles. Ooh, okay. Here in the picture, the first picture, you can see like the table. It's main like comparison of the classical optical communication and the quantum communication in the theory. Let me just read it. Okay, for the classical communication to the communication channel, we have any optical transparent medium, including optical fiber and free space links. And for the quantum communication, any optical transport medium, including optical fiber and the free space links. Basic. Uh, the both of them equal, yeah. For the communication channels. Uh, for the light source. For the light source, we in the classical communication have only laser and the infrared light source. And for the quantum communication, we have both of them, like laser incoherent light source, and also we have the single photon source, squeezed state of light, and the entangled light. For the information coding, in the classical communication, we have activity encodes classical information and orthogonal states of light. And for the quantum communication, we have the actively encodes classical or quantum information on orthogonal or non-orthogonal states of light, possibly generate information during measurement process. And the next one is the photon detection. For the photon detection in the classical communication, we have the phase insensitive intensity detection and the phase sensitive coherent detection. And for the quantum communication, we also have the phase intensity single photon detection and the phase sensitivity coherent detection. Here, the single photon is the main difference. It will have the work of the some photons, yeah. And channel loss management. Uh, for the classical communication, we have bright light pulses, optical amplification, classical regenerators. For the quantum communication, it will be like quantum repeaters. Let me just remember what is quantum repeaters. Quantum repeaters. It's like some tools that repeat the process of the uh, transmission our information. Yeah. Uh, it's also help us to uh, share the quantum states on the big distance. Yeah. And what is the main advantage of the quantum repeaters is that we don't have the loss of uh, like the voices. Yeah, like we have the voice, for example, my voice, and there will be some noises. Yeah, the main advantage is that we don't have the noises. Like in the Russian, it will be the belly shum. I think you get it. Okay. For this table, it's all. It's as you see, we have uh, the bigger advantage of using quantum communication systems than the classical communication. And here, yeah, also information about quantum repeaters and the key difference. Let me read the just key difference. Information encoding classical communication uses discrete states. Quantum communication uses non-orthogonal quantum states. You see it in the table under no cloning theorem. Quantum states cannot be perfectly replicated, preventing classical amplification and regression. Qubit, yeah, I also said before about the qubit. Okay, let's move on. And the Haleva bound limits the amount of classical information extractable from a quantum states, despite qubits theoretically holding defined classical information. For the quantum repeaters, also we have here the picture that compare the first generation of the quantum repeaters, the second generation of the quantum repeaters, and the third generation of quantum repeaters. And as I know from this article, in the future, we will use only the second generation and the third generation of the quantum repeaters. These devices, for example, uses in the quantum computers. I guess you uh, heard about this before. Quantum computers for the some the complex calculatings. Yeah, like for example, the particles in the space and so on. And these devices helps to it. And the main advantages uh, I said before. This okay. I guess we need to move to the next slide. Yeah, here is like the picture which uh, give us some definition and understand of the QKD and how it works. QKD, as I for sure, is a prominent near-term quantum communication application that allows two remote parties to establish random cryptographic keys using in secure quantum channel and an authenticated classical channel. It does not require deterministic state transmission or quantum repeaters, making it feasible with current technologies. For example, the analog of the QKD we have right now, but its work more complex. It's called like blockchain. Maybe you heard about it. It's like the systems for the passwords and for example, the Bitcoin also works in the by this blockchain. Uh, for example, we have credit cards, yeah, yeah, cards, and uh, I don't know how you this function on your banks, but in the as I know Kaspi and the BTK, for example, we have the dynamic passport like CVV on the other side. Yeah, like three symbols on the other side of uh, the bank card, and the blockchain works uh, by yeah this rule that we have the dynamic passwords. It's how works the blockchain uh, and the QKD which work more better because as I said before, it's like have some the effect of the to the quantum states for the superposition, and our technologies will be like more complex, uh, but in the best in the other hand, it will be simpler than we have right now. And how it works? You have the just a picture here. For example, we have in this building is Charlie, in this building Bob, and the source like Alice. Alice sends to the Bob single photonic quantum states encoding with random numbers. Any attempt by an adversary to intercept these states initially disturbs them, which Alice and Bob can detect. This allows them to estimate areas information. And the practical advantage, QKD does not require deterministic quantum communication and can be implemented without quantum repeaters. Error correction and privacy amplification are performed classically, simplified implementation. And the main advantage is like the security. The security of QKD is rigorously analyzed based on quantum physics, making it immune to computational attacks. Practical implementations address side channel attacks through devices independent and semi-D protocols like MDI QKD. Okay, let's move on. I guess yeah, this one slide. The high cost of replacing existing optical fiber infrastructure necessitates integrating quantum communication protocols into current fiber networks. This approach leverages existing infrastructures and address challenges like noises and devices incompatibility. Yeah, here about some information of the coexistence of quantum and classical signals, the quantum incompatible devices, and the simulation and transmissions. I guess the more interesting is the coexistence of quantum and classical signals. VDM technology enables sharing fiber resources between quantum and classical signals, noise photons from classical channels are multi-gated through wavelengths assignment, filtering, and power control. CV quantum communication protocols with optical coherent detection and promising due to their mode selection capability. Okay, we don't have enough time. Let's just move on to the next slide. And it's the future outlook hybrid quantum internet. Okay, the first one is the challenges and the solutions. Um, Transmitting quantum states through lossy challenge deterministically remains a challenge due to no cloning theorem. While quantum repeaters are under development, near term solutions involve probabilistic protocols like QKD integrated into existing fiber networks. Um, Next one is technological advancements. The pursuit of quantum internet will drive innovation in integrated photon sources, quantum memories, and quantum repeaters. Simulationally, classical optical technologies will advance, leading to low noise receivers, ultra low loss storage, and novel fibers. Next one is the quantum to classical translation. Quantum networking technologies such as a low loss optical circuitry and all optical signal processing will benefit classical communications by improving energy efficiency, reducing latency, and increasing bandwidth. And intelligent cited communication. Utilizing pre-shared intelligence can significantly enhance classical communications rates, potentially surpassing the Haleva Schumacher Westmoreland bound, marking a transformative shift in communication theory. And as a like conclusion for this is the Internet of the future will be a robust, versatile, and a transformative global communication infrastructure thoughtfully designed to integrate the best of both classical and quantum worlds. Okay, this is the end for my presentation. Thank you for your attention. Ask any questions. Yasha.
So, thank you for presentation, and I have questions. So, if really I still don't really understand what a hybrid classical quantum network is it basically the normal internet with the same quantum technology added? And why can't we just build a fully quantum internet right away?
Yeah, thank you for your question. Uh, yeah, as I said before, the quantum communication layers, we have some disadvantages of fully using quantum internet right now, because it will be too expensive to replace the internet that we have right now. The first problem is that replacing the first is the internet that we have right now. It will be more expensive, and the next one, it's the time. Yeah, for example, for me, difficult is to live without internet for the one day, and you just imagine that you will just wait when they fully replace the quantum internet. Uh, it will be like took for the 5 or 10 years, I guess.
Thank you for your answer.
Okay. Uh,
Okay, I also have a question. Can I ask?
yeah, yeah, yeah.
Okay, my question is why are not hybrid quantum networks used everywhere yet, and what technical problems are stopping them from being widespread?
Yeah, yeah, thank you. Let me just think. I guess I don't say it, yeah, in the presentation. For the any information loss, we also have, for example, photon loss. Yeah, photons disappears after the range about the 50 to 150 kilometers in the optical fiber. Next one is, for example, the lack of quantum repeaters. Classical networks use uh, amplifiers, but quantum signals cannot be like copied. Uh, so next one is the we have just problems with the synchronization issues. Yeah, the classical and the quantum channels must be like perfectly synchronized in time. And another one, the just problem is that the high cost of equipment. Eh, the main problem is that money. Yeah, we don't have money. Yes, I answer to the question, and you understand.
Okay, thanks.
Okay. Uh, Sambat, yeah.
First of all, thank you for the presentation. I think it's a really interesting article. And my question is, can you explain in simple terms what the difference like between the classical channels and the quantum channels, and what exactly is being sent through each of them?
Uh, okay, thank you for a question. Like in the very simple way, the classical channel like we have right now, it's carriers on ordinary information like text, videos, files, commands, routing information. This everything the regular internet already transmits. And for the quantum channel, the carries quantum states of photons such as uh, quantum case, which means QKD, integrated photons, and the quantum bits, like qubits. And the key difference is someone tries to intercept a photon, its quantum states collapse, and the system immediately detects the intrusion. So the quantum channels is used not to send like the some data, so like text, video, uh, like images, but to provide secure key exchange and quantum level security.
Okay, thank you for the answer.
Okay. Any questions? Okay, thank you. I guess we end.